All right, the next section here in chapter 12, capacitors. We're going to look at a device that stores energy. Basic capacitors, types of capacitors, how do we handle capacitors in series and parallel, and looking at capacitors in DC circuits. So our objectives follow that. You can take a look at the objectives, the typical analysis and discussion. Understanding terms, what is a capacitor, what is a dielectric, the unit for the capacitor, the farad, and then we'll end up with something called the RC time constant. A capacitor is a passive electrical component that stores electrical charge and has the property of capacitance. Okay, so it stores energy. The basic construction then of a capacitor, if we look at it in truly its most fundamental makeup, we've got two plates, two leads, and something called a dielectric stuffed in between those two plates. So a capacitor is an electrical device that stores electrical charge and is constructed of two parallel conductive plates separated by an insulating material called the dielectric. Connecting leads are attached to the plates. A basic capacitor is shown in the diagram. So this is very, 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 very basic. Most capacitors are not constructed this way, but if you put something like this together, it can be construed as a capacitor. How does a capacitor store charge? In the neutral state, both plates of a capacitor have an equal number of free electrons, as shown in the diagram. When the capacitor is connected to a voltage source through a resistor, electrons then move from one side and the other side to start building up a charge. Okay, because of that dielectric, the movement of electrons are not allowed to move through the material. That's not to say it can't do it. You put enough energy on both of the sides of those plates and you will get current flow. A charged capacitor then acts as a temporary battery. If you get a big old electrolytic capacitor and put a charge on it, it will hold that charge for some time. Sometimes a charged capacitor can be used as a temporary source for devices. So capacitors are capable of storing electrical charge for a long time after power has been turned off in a circuit. So you must always be careful when touching or handling capacitors in or out of a circuit. If you touch the leads, you may be in for a shock as the capacitor discharges through you. And there are a lot of high energy devices like power supplies that have huge capacitors in them. And the whole idea behind that is for them to store energy. So if we look at this diagram, we get a depiction here of just exactly what we've been talking about. We've got leads on both sides of the plate and a dielectric in between. And you can see if we put the capacitor on a battery, it starts to distribute the charge onto both sides of the plates. What happens then is you'll get to a balance. The charge will cease to occur because the electrons will cease to occur, and you'll have a positive and a negative side of the battery. So ideally, a capacitor retains its charge when disconnected from the voltage source. Capacitance then, used as a unit, the amount of charge that a capacitor can store per unit of voltage across its plates is its capacitance, and we designate it as C. That's not the unit. The unit is the farad, but we designate it as C. So capacitance is a measure of the capacitor's ability to store a charge. The more charge per unit of volume that a capacitor can store, the greater its capacitance. And so we can create an expression here that's a ratio of charge to voltage to define capacitance. By rearranging the terms then, we can see that we can come up with charge, capacitance times voltage, or we could come up with voltage, charge per unit capacitance. So the unit of capacitance then, as I said before, is the unit called a farad. It's the basic unit of capacitance. Recall that the coulomb, though, is the unit of electrical charge. So by definition, 1 farad is the amount of capacitance when 1 coulomb of charge is stored with 1 volt across the plates. Most capacitors that are used in electronics work have capacitance values that are much, much smaller, and we use microfarads and picofarads, which in the old days we called microfarads. A microfarad then is 1/1,000,000th of a farad. So we can see that in the mathematical expression, 1 microfarad is equal to 1 times 10 to the minus 6th farads. And a picofarad is 1/1,000,000th of a farad, or 1 times 10 to the minus 12th farad. If we look at the table, we can see conversions for micro and picofarad. So this is worth noting. Again, something to put in your notebook so you can keep track until you learn and become very familiar with these relationships. So a couple of examples here. A certain capacitor stores 50 microcoulombs with a 10-volt source across its plate. What is the capacitance in units of microfarads? Okay, we've got a 2.2 microfarad capacitor that has 100 volts across its plates. How much charge does it store? And C, determine the voltage across a 1,000 picofarad capacitor that's storing 20 microcoulombs of charge. So by using the same expression, move the terms around for charge, coulombs, the value of energy and the value of voltage, we can see that the capacitance then is equal to the charge divided by the voltage. 50 microcoulombs divided by 10 volts gives us 5 microfarads. For B, the charge is equal to the capacitance times the voltage, or 2.2 microfarads times 100 volts, 220 microcoulombs. And finally, the voltage then for part C, the charge per capacitance, 20 microcoulombs by 1,000 picofarads gives us 20 kV of voltage. Example 2, convert the following values to microfarads. So in each case, we can see we've got a very small value, 0.00001 farad, 0.0047 farads, 1,000 picofarads, and 220 picofarads. So they want us to convert all of these to microfarads. So in part A, we've got a value of 0.0001 farads. We're going to multiply that times 10 to the 6 microfarads per farad, and we get 10 microfarads. For part B, we do the same thing. The conversion factor then being 10 to the 6 microfarads per farad, we get 4,700 microfarads. For C, 1,000 picofarads, again using the same conversion, 10 to the minus 6 microfarads per picofarad gives us 0.001. So notice we changed the exponent here to get the conversion relationship that we were looking for to change picofarads into microfarads. And finally, 220 picofarads, the same conversion gives us 0.00022 microfarads. Okay, so the key to the conversion is in choosing the correct conversion relationship. Example 3 then, the following values are in picofarads. So now we need to adjust our conversion. So in the first one, 0.1 times 10 to the minus 8th farads, we're going to use the conversion 10 to the 12th picofarads per farad gives us 1,000 picofarads. In part B, 0.00022 farads, again, 10 to the 12th picofarads times farad divided by farads gives us 22 times 10 to the 6th picofarads. Again, you can run this through your calculator and calculate. Or you can pull out a piece of paper and do your cancellations and your unit values with the exponentials to make this happen. So again, back to the basic capacitor, how a capacitor stores energy. A capacitor stores energy in the form of an electric field that is established by the opposite charges stored on the two plates. So you can see here again, although it's showing here these lines of force between the two plates, there's no movement of electrons across that dielectric, but there are lines of force, okay, and that is an electric field. The electric field then is represented by lines of force between the positive and negative charges and is concentrated within the dielectric. And we're going to learn a little bit later what kinds of things form dielectrics. Dielectrics are specifically made not to have current flow. So the plates in the diagram have acquired a charge because they are connected to a battery. This creates an electric field then between the plates, which stores the energy. So you think about this, although there's no current flowing between the two plates, they're building up electrons and protons, more positive, more negative. The energy stored in the field then is directly related to the size of the capacitor and to the square of the voltage as given by the following equation. So we have a relationship here for the stored energy, W, is equal to 1/2 the capacitance times the voltage squared. For those of you that have taken the first physics course, that relationship ought to be kind of familiar to you. When capacitance is in farads, the voltage is in volts and the energy, W, is in joules. So how do we rate a basic capacitor? Every capacitor has a limit on the amount of voltage that it can withstand across the plates. Again, you put enough voltage or potential on those plates, you will cause current to flow through the dielectric, and that's not what you want. The voltage rating specifies the maximum DC voltage that can be applied without risk of damage to the device. If you start getting current through the dielectric, you're going to damage the device. So there is a threshold. If this maximum voltage, commonly called the breakdown voltage or the working voltage, those are the thresholds, if it's exceeded, permanent damage to the capacitor will result. For those of you that are in the labs and you start taking a lab and you experience this, your lab instructor will tell you that when it happens and you get a puff of smoke come out of the capacitor, they like to joke and say, you just let the smoke out of the capacitor. So you must consider both the capacitance and the voltage rating before you use a capacitor in a circuit application. The choice of capacitance value then is based on the particular circuit requirements. The voltage rating should always be above the maximum voltage expected for a particular application. So what determines this? Well, something called the dielectric strength determines that. The breakdown voltage of a capacitor is determined by the dielectric strength of the dielectric material used. Again, we don't want current flowing through the dielectric. The dielectric strength is expressed in volts per mil. 1 mil is equal to 0.001 inch, which equals 2.54 times 10 to the minus 5th meters. Okay, write that down in your notebook. Keep track of that. Table 212 then lists typical values for several materials. Exact values vary depending on the specific composition of the material, and these things can be made of lots of different materials. Capacitor's dielectric strength can best be explained by an example. Assume that a certain capacitor has a plate separation of 1 mil, so that's 1/1000th of an inch, and that the dielectric material is, in this case, ceramic. This particular capacitor can withstand a maximum voltage of 1,000 volts because of its dielectric strength is 1,000 volts per mil. Okay, and we just extracted that from what was given. If the maximum voltage is exceeded, the dielectric may break down and conduct current, causing permanent damage to the capacitor. You let the smoke out. Similarly, if the ceramic capacitor has a plate separation of 2 mils, its breakdown voltage is doubled, 2,000 volts. So take a look at this this chart here on the bottom and get an idea of what kinds of dielectric strength there are depending on the material. So before we go on to the temperature coefficient, let's go ahead and stop here and we will regroup with the next set of requirements and characteristics.